Okay, so thank you very much, and thank the organizer for giving me this opportunity. So I will talk about rational dynamics on the projective line of the field of p-adic numbers. This is a work joined with Shilei Fang, Hongmin Liao, and Yue Wang. No, you see, I take the page, I think, right?
Yes, we can see.
Okay.
Yeah.
Okay, good. So it works. So this is my outline of the talk. So I will give a very short introduction, and then I will talk about two different kind of dynamics on QP. So one is one if it's another is expanding map, and then I will go to the work where we are preparing the paper. So it's about the geometric finite rational dynamics. And to just illustrate the theorem, I want to talk about an example. So let me just start, a little bit. I will not recall you what is the p-adic numbers, but maybe just a little bit the projective line of QP. So this is just like the same thing, the projective line over R. So you take a couple of points in QP, not 0, 0, ready? So we take this, if this is, you have some proportion, same proportion, then I call this couple and another couple are equivalent. And if you just modulo this relation, you get the projective line. And on this projective line, we can define the spheric metric, the definition like this. And one point to look at the projective line is just to look at the, you put the infinite points on your QP. And that is, so usually we can look at the two different points on QP like this, and you will see from this formula, if your distance from 0 is less than 1, then it's the same matrix, the distance, if both of two are in ZP, it's the same. But outside the ZP, you should change a little bit. So this is just the formal definition, but maybe you want to see what's the shape of this projective line. But firstly, I want to recall you this tree representation of the field of p-adic numbers. So this is ZP, and you for each you have p balls, and then you have or for each small ball you still have p balls. But outside ZP, you will look just a little further. The bigger balls is still this tree like this and go to infinity. So what is the projective line? Projective line, you should look at the infinity as some common point. So one idea is just you to take this part is the same thing as other parts. So just like we take then some the projective line of R, you take the line and you join the infinity, and then you get the unit cycle, right? And then you take, it's the same thing, you take just this line this way, and then you will get, so this is your ZP, and this is another branch outside ZP, and you take this branch, is the same thing as this, and then you get your projective line. So this is the shape. So this is from here you have J2, and this is outside J2. Outside J2 you have one branch which stands for the infinite points. Yeah. So in the infinite point, you should look at some other like the other points, the same point. So the boundary of this tree is the projective line. So another model is this one is for p = 3. So so I will talk about the dynamics on this projective line basically. But so for me, dynamic system. So it's a space and a transformation. So this space is p-adic space, surely. So for this p-adic dynamics, so at the beginning, I think these three works are very important work for the very beginning of a dynamic system. And in this talk, so you will see the here what which for the p-adic string theory. So I think in this conference, you also there are many theory about this string theory. So but for me, I just want to study the polynomial in the rational maps. So polynomial rational map, I will study like dynamics on the JP or QP or the projective line or QP. And here I want to begin with the two family. So this two family is one is we call it one Lipschitz. So the one Lipschitz property. So the distance of the image of x and the image of y is bounded by the distance of x and y. This we call the one Lipschitz. But another contrary. So if the distance becomes bigger, then we call it expanding. So these two different systems will you will see the dynamics are quite different. So to begin with, I just want to give you two very simple example to show these two different dynamics. So one is just you take this transformation, this polynomial, the order 1, x plus 1. So this is a transformation defined on ZP. And so to study the dynamics, you want to study the orbit. So you want to know a point with this iteration where the point will go. So one property we call it minimal. Minimal means every orbit. If you take any point and iteration, the orbit will be dense in your space. That means the point with this iteration, you will go everywhere. So this is a quite important property. And you will find this simple polynomial is exactly a transformation, minimal transformation. So to prove it's just the, the closure of n is JP. When you iterate, then just a +1, you will get the n. And the closure of n is JP, and then that means the orbit is dense in your space. Then this is the fast, very fast example for one Lipschitz dynamics. And usually we need to study the minimality. Another one is expanding. So if you take this polynomial divided by p, divided by p, then the distance, if you calculate fx minus fy, then you will have expanding, your distance will expand by p times. And here, maybe I just, in this dynamics, usually we use the shift on a symbolic dynamics. So this is to describe your dynamic system. So if I want just to draw something, so ZP, you have p balls. You have p balls. And in fact, for example, here, this transformation will send each ball to the whole space. So the whole thing is ZP, right? So each point, you will take this kind of something like 1, 0, 2. You just take the one ball like a symbol, and that means your one symbol will go to every other symbol. So this is we use this shift, use the symbols to describe this dynamics. So this is just a sequence of symbols from 0 to p minus 1, and the shift is just you just delete your first symbol. This is the shift. So basically, from usually we understand well the symbolic dynamics. So that is why we use the symbolic dynamics to describe the usually expanding dynamics in QP. So I should delete this. Then I can turn the page. Okay. Oh, I should I should erase all. So how can I erase all? Yeah. Okay. Good. So yeah, just you in your mind, you can see there are two different dynamics. One is minimal. Another one is symbolic shift. And this is symbolic shift. In fact, is some positive entropy system, and this minimal is zero entropy system. And this one we usually all call as the chaotic dynamics. So chaotic usually positive entropy expanding. And one Lipschitz is minimal and zero entropy. So let me just detail a little bit or these two different systems. So first one is one Lipschitz. So one Lipschitz usually for a polynomial with the integer coefficients, with the coefficients in JP, and then you will see your system will send a JP in JP. So this defines a dynamic system. And this dynamic system is one Lipschitz because if you take the difference of fx minus fy, then your constant term will be cancelled. And then there are many terms which you will find something x minus y like the common factor and other parts, but other parts is integer coefficient. So this is in JP, then you will see the distance, this one is smaller than 1, and then this is one Lipschitz, right? So it's just an easy fact. But for this one Lipschitz, then if you have this property, then you will find that you have equal continuous property. So that means if your xy is less than delta, and the distance, this is an equally, you will have all the iteration less than epsilon. So for this family, there's one thing very important is if we, usually I call it minimality. So transformation is minimal. It's the same thing with the ergodicity with respect to the Haar measure. So many people also call it ergodic. Voila. So it is ergodic in some, on some part or not. But for me, in this talk, I will always talk about minimality. But minimality is the same thing with ergodicity. Okay, so let me just restore and then turn the page. So for this study, you will find many people on these topics. So you will find here, for example, as Diarra Sila. So Sila will talk later. And this is for polynomials. So there are many polynomials, and I will further talk about the polynomial things a little bit later. And for Mahler series, this is Anashin begin with this study, and later you will find the work of John. And I think today's last speaker is John. And also you will find the work of, I don't know how to well pronounce, but Memich maybe. And then this is for using the Mahler series to study the one Lipschitz transformation, and one can also use the Vanderpoort series to describe the one Lipschitz transformation, usually to describe the ergodicity or equivalent to minimality. So you will find many works of Anashin, Kennikov, Yurova, and also John. And another thing is a T function, also studied by Anashin and some Chinese guy. So I will further a little bit, introduce one of my results is about the minimality of polynomial. So we can prove for any polynomial with degree less than 2, I can describe in a general picture of this dynamics. So this dynamics, I will divide the space into 3 parts. The first part is just the finite set of periodic orbits. So periodic orbits, so one thing important is you can only find finite many periodic orbits. And the second part is some union of minimal parts. So each part is minimal, and each part is just a finite union of both. So you have finite union of both, and on this part, your orbits will be dense on this part. So let's just you have some finite number of orbits. You have some minimal parts. So minimal parts, that means if you take some point, and then the orbit will be just go in this part, will be dense. If you take another point here, and it will go like this. And there are some another parts, is the attracting basin. There are something just goes to here or attracted by the periodic orbit. So this is the general picture of this dynamics. So very important is the one-if property. Another property I used is the Taylor expansion. So this idea, it works also for for another work transformation. For example, I have a work on linear fractional map on the projective line in the power series. And also we have one thing for rational map having good reduction. And in this direction, for some special polynomial, for example, Chebyshev polynomial or square mapping, I have some work. And you can also find quite recently, there is a group of Korean specialists. They also study this minimal decomposition. Yeah, so just to give you 2 pictures, this is one example. Your polynomial is just +3 for J3. And J3, you will find you have 3 minimal parts. So if you take a point, then it will go here. But another one is a little different. So just a 6x. And then in this dynamics, each sphere, you have three minimal parts. And this things I call it 1 minimal part. That's 1 point will go there, go there, go there, go there, and length here. And for other sphere, you will have the same copy of dynamics. Here you have 3 minimal parts, and the second sphere, you still find 6th sphere. And the same thing. And in the center, in fact, is the fixed point. The fixed point 0 inside. So this is a very typical decomposition of ZP. This is just a very simple polynomial. Why we study this? So one maybe in number theory we can apply is this theorem. So this theorem we can use to calculate the frequency. If you have a sequence like this kind of sequence, a power n, c minus b, this is the sequence. You want to find how many, the first n numbers, how many are divisible for by this p to power k. So this frequency we can use Beckhoff theorem to calculate. So how we can use? You just take this multiplication polynomial, and then divide this is equivalent to say your orbit is in this balls. So the Beckhoff theorem can tell you how the frequency this your orbit will goes to some balls. Yeah, this is this thing. So for example, the Fibonacci number, the sequence of Fibonacci number, you can also use these things to calculate. So yeah, this is one application. So for the second family is expanding things. So for expanding things, so in general, we study this kind of continuous differentiable function. And this is just some formal definition, but usually the analytic function, the polynomials in the rational map all satisfy this kind of property. And this property, quite important, that is when you take a small ball, in a small ball, you always, you know, in the real situation is smaller than, but here it's always equal, then that means you the dynamics in locally is some scaling. It's just a scaling, quite simple. It's nothing, it's scaling. So this property is quite important in the p-Adic case. Well, before I state the some results, I will just tell you that there are many also many people studying this expanding dynamics. Then I think also, for example, in the audience, you can find Mukhamedov, many works, and also Zenonov, some p-Adic Baker's transformation. Yesterday speaker, Fourneau, and yeah, so Kakimov, maybe in 2 days he will speak. And also I study these things with Ahmad, my student, with Sablov. Yeah, so this is just, I give you a list of many works. So let me just show you in general, well, we can find some family of polynomial or rational map which has this interesting property. So let me just, well, I studied some dynamics on some compact open sets of QP, and I suppose these two properties are satisfied. So the inverse imagine of this X is included in X. So I need to study the dynamics on X. So I should firstly have this. Another property is quite important, but basically I showed you many transformation, many polynomial, any polynomial in rational map, they satisfy this kind of property. So that means I can decompose your compact open sets into small balls. I want to decompose into the same size, well, the same size of balls. And in each small balls, you have scaling property. You have this scaling property. Then I can define the field Julia sets like this. And then I need to study the expanding property. So I call this weaker repeller. If you have positive, that means you have expanding, and you have rarely expanding things. That's at least you have one strictly positive. But if you all positive, I call this repeller. So this is my system, and then I can study this system by symbolic dynamics. How I study it? So I just, you know, one in QP, one ball, if you, the intersection is non-empty, then one is included in another part. So, so here I need to define a matrix. So if you, that means I will call the balls, you know, the balls, the symbol. My small balls is the symbol. It's just the same thing as I explained it to you. So you have symbols. If one symbol goes to another, I will take the matrix 1. If not, I will take 0. So this is the same thing. If you more familiar with the Markov chain, it's the same thing. You take the state. If the one state goes to another, you take some arrow from there to there, and this arrow defines your transition matrix. It's the same thing like a Markov chain. And here it's the same thing. If this matrix is irreducible, I call it the system is transitive. And then I will use this this thing is that the shift. So here maybe I need to just add a little bit, because later I also use these things. So here sigma A is just the set of symbols. So I have some symbols which, you know, for example, I have symbols x0, x1, x2, these symbols. The symbols satisfy this property from x0, xi to xi plus 1, you are allowable. So you have a path from I to I plus 1. So this is all the possible paths. This is just, if you, well, and then the shift is the same thing. Shift is just you take your sequence, and then you just delete the first one. This is your shift. So the theorem says this kind of expanding things, in fact, it's the same thing. So we call it topology conjugate. Is just mean that means you have a system here. You have a system F. Then you have a commutative graph. So this is your shift. So yeah, so you have a H here, conjugate. You have this graph is conjugate. Then all the things of dynamics is the same thing like this dynamics. So that means I describe my p-adic dynamics by using some symbolic dynamics. So let me just attain. Well, so maybe just this is just two example. You know, I just recall you at the very beginning. Take the same thing, but with m equals 1, and m equals 1 and a equals 1. In fact, it's the work of Woodcock and Smart, and we can do this for more general family. And in this direction, in fact, we can find many applications on p-adic Gibbs measure on Cayley tree. So you can find many works of Mukhamedov, and I also have a work here. So in fact, usually if you can prove your I will talk about a little bit. This is the Betty mapping. If you have a subsystem which conjugates to some subsystem of finite type, and then you can find many periodic orbits. And in this case, one periodic orbit corresponds to one periodic p-adic Gibbs measure. That means if you can have some kind of this subsystem, you can prove there are many p-adic Gibbs measure. Yeah. Okay, so let's just go to the something new. Yeah, so before I talk about my results, I also want to mention there are many works on the rational maps, but many works they study usually you know, for some special family. Here you can find many special family, especially there are many works of Lozikov. But many of these works usually and include also the work of Dragovich, Kennikov. They study basically the first thing is the fixed point and the periodic orbit, and then they describe the zero disk. But there are not so many things who cares about the really expanding case? I mean, if we can find some subshifts inside. And especially what I will talk about is something, if your rational map has some critical points. So I will talk about this later. Firstly, to do this, usually we divide a dynamic system into two parts. One part is the far two set. Far two set is the dynamics, is equal continuous. The family is equal continuous. This I mentioned a little bit at the beginning. So you will find this part, your iteration is equal continuous. Then you will find that this is something like one Lipschitz, and that is something usually I need to describe. So one Lipschitz usually on the far two set is one Lipschitz, and these things usually I need to use the minimal decomposition to describe. Another part is Julia set. It's a complement of the far two set, but in this part, usually your dynamics is expanding. And in this situation, usually we need to use the Markov shifts to describe the dynamics. Yeah. So again, this is why at the beginning I talked about the two different dynamics, because usually your dynamics exactly you have two different dynamics. One is far two set on far two set, another on Julia set. So here, let's just study, well, the minimal decomposition. We usually have some methods to do how to describe the minimal subsystem. But for the Julia set, there's still many difficulty. One thing is exactly the existence of critical point. So if there is no critical point, basically I think the work I described for the subsystem finite type is enough. We can describe usually, but if you have a critical point, there are some difficulties. So I will mention an example later. So here, a little bit general, you can study some finite extension of QP. And well, usually rational map, I need to work on also the infinite points. So usually I work on the projective line. So so I study the rational map on some finite extension of QP. And I will, so in the Julia set, you can find some critical points, which is a better case, a better situation. So how to treat this situation. So, and another thing is there some, the definition of grand orbit. Grand orbit is you have some critical points. So you have a critical point, you have some critical orbit. So it will goes. And the grand orbit is when you look at, this is your critical point. When you look at the orbit before and later, you can see the another things will goes to this one. So there are some point Y, some point will meet the orbit of X. So this is all this family of this set of points we need to delete. So we need to delete. So this is better things. If you just kick off this part, but again, I need some condition. I could not treat everything. So I call it the transformation is geometrically finite. So that means your critical orbit, you could not go further to infinity. You have only finite many. For example, if you and then go back, well, that is a finite many. You cannot go infinitely away. You just from some point we'll go back to this orbit. So only finite forward orbit, and then for this family of transformation, we can describe. But I need to use infinite many symbol. So this system is topologically conjugated to some countable states of Markov shift. So here I also have some matrix, and this matrix should be some infinite matrix. Yeah. So let's just go to some very special example to see how this works. Oh, yeah. So yeah, so just this example, it's some polynomial. It's just some polynomial, cubic polynomial. It's not so easy. And I take p equal 2. I take p equal 2. So what happens for this example? Let's just study a little bit. So first thing, as everybody studies, so we should look at the fixed point and the critical points. So fixed point, you will find 0 goes to 0. So 0 goes to 0. One set you can calculate. One set goes to calculate. And infinity, evidently, infinity also some fixed point. And the critical points, you can just calculate the derivative. So critical points, I just recall you, critical points is what it says, just the f derivative equals 0. And also you can calculate, one is you calculate the derivative, you have the least factor, and you will find one is the critical point. And you will find all 3 critical points. And so their critical points are better things, because your derivative is 0. So you have some, basically you have super attracting. So everything, you have very strong attracting property. And here, 0, you will find 0 is some repairing fixed point. So just along 0, you have expanding property. So why this polynomial is quite strange is basically this one. 1 is critical point. So here on 1 you have super attracting property. So super attracting property like here, but this is not a fixed point. But 1 is goes to 0, go to some repairing property fixed point. So that means here the system contracts, but even so, there are 2 points. Maybe there are some points go to here very close, but if you go to 0, 0 expanding, so the orbit will go very large. You have expanding. Just if you go close to 1, something goes closer, but if you later the distance will be larger. So that means you have some points close and then very far away from each other. So this is something difficult to control the system. Another 2 parts are much more easier, but this is basically this causes the problem. And why this polynomial? So this polynomial, in fact, there are not so many. In fact, here, if you look at the cubic polynomial, you have only 1 like this, and this is exactly I gave you here. This is the only 1 cubic post-critical. This is the forward orbit of the critical. This is critical point. You have, this will go to itself. Then this is the fixed point. So the orbit is finite. Here I use, maybe you will see what this. This is just means this is a map 2 to 1. This is a map 2 to 1. This is the map 3 to 1. So 3 points will go to 1 point. in the neighborhood of these ones. So you will see you have some difficulty here. So the idea, in fact, is to decompose nearby this point. You need to decompose infinitely many balls, and these small balls will be your infinite many states. And this is you will define some Markov chain, but with infinite countably many states. So let's just go a little further to look at this. So just this polynomial. And well, the first thing is what is the Julia set Fatu set? Yeah, so this is Fatu set. This I call it Julia set. So this one notation is you have one point in the Fatu set. You have a component. So nearby all these are all Fatu parts. And the Julia set Fatu set we can find it. So this is Julia set. Just the inverse of the union of two balls, and here is near the neighborhood of infinity and the neighborhood of one set. You have, you know, if you go back, these 2 points are good things, are super attracting but fixed points. So usually, if you go close to these 2 parts, there's no problem. It's your Fatu set. So the difficulty is how to study the Julia sets. Yeah, so that is, I need to study a little bit how the ball moves. One easy thing, outside J2, well, I take P equal 2. Outside J2, well, nothing to do. It goes to, you know, this is the Fatu part. Fatu part nearby the infinite point. And these 2 balls, you do not need to study. It's also Fatu parts. And why these 2 Fatu parts? This is just more details, but these 2 balls go to near to one side, and another goes to near infinity. The difficulty is to study the, you know, nearby 0. So nearby 0, near 0 is expanding fixed points. So near 0, you have expanding things. And I just described how near 0, how the expanding ratio is always 4. Yeah. And then a little further. So I just describe more in details the nearby 0. So this is nearby 0. It's 2 to power 2n. And there are many things. There are some calculations. You can just use the map. You do some calculation. You will find this family. You do not need to study because finally you will go to Fatu part. Well, this is near 0, and especially this one. I will go back to this formula. So this is 2. This is 4 plus 2 to 5 Z2. The image is these things. So 0. There are some parts also goes to, you know, the neighborhood of 1. So this is close to 1. If you take m goes to infinity, the same thing. There are two balls. Well, another part is near 0, near 1. How it is. So near 1 is a super attracting. You have many attracting property. So the attracting ratio is, you know, like this. So I also describe this. So how this near 1, how the ball will go. And then I will give you a graph, how the balls moves. Now I just care about the Julia sets. The Fatu sets I will just put it aside. And you know, I take this to be balls, but the balls are symbols, my states. And I use this graph to show you how these balls move. That means how the state will go. And then I have two, this is close to 1, B prime close to 1. So the close to 1 will goes to close to 0 because the 1 goes to 0. So goes to the balls of 0. And the 0 is expanding. So it will go like this, expanding like this. And this also expanding like this. But later here, the A1 prime will go to this one and then go to A1. A1 is that I just tell you that I will go back to this one. And in fact, this one, how it moves like this. This is, I just copied the formula here. I just copied the formula here. And what's this? This is close to 1. That means this state will go to this state. Okay, so you have this sequence of states, goes like this. And when you go here, and if you go back to this B, goes to here, but not here, but not B1, goes to union of this one, and with 1. And then another things, you know, these things, these some tails, all goes to this. Then these tails, I do not care. That is now I need to construct my matrix. So I call this states. You have this state. And there are some special states, 0s and 1. You know, I have this 1 here, very special states. And 0 also is from fixed points, it's also special states. So all are states. And if one ball goes to another, I take some matrix like defined like this, just as before. Well, and then with this matrix, you will define some shifts. And I just still recall, so this alpha 1 ball, A1 ball will go to the B balls, like this. And the infinite 1 goes to 0. 0 is fixed point. So then I can define the matrix. But to define the matrix, I need to just kick off the non-interesting parts. You know, there are some tails I will just kick off. So I will kick off, just to go back a little bit. I will kick off this part because all these things go finally to here, and here goes to the union of this one. So I will kick off this. So alpha prime, I will kick off. I will just keep the B, beta and the beta prime in the alpha. So this is, I need to keep alpha and beta prime states. And then I use from one ball to another, and I use this matrix. And this is the dynamics. This is dynamics. And for one dynamics, you want to know the entropy, how to calculate the entropy for infinite matrix. That is, now you also know this is some definition of Greenwich entropy. And the definition is just the supreme of all the subsystem restricting to some finite sets. You can calculate the supreme. And then this is the method how to calculate the entropy. You need to count the number of loops. So if your graph starting from 1 point, you go back, you have 1 loop. You calculate how many loops with the length n. You then calculate, you construct this series and use the root of this 1 minus this series. This is R, and then you take minus log R, you will find the entropy. And for our case, we just, here the least proposition is if you can find R, it does not depend on which symbol you start. Then, for example, I just go a little bit. Yes, how to count this entropy. So in fact, I use alpha 1. So alpha 1 goes to beta 1, beta 2. So beta 2 will go, beta 2 will go alpha 1, alpha 2, and alpha 2 will go back to alpha 1. This is 1. And also another is alpha 1 goes to beta 2 prime, beta 2 prime go to alpha 2, alpha 2 go back to alpha 1. There you have the length 3, the length 1, 2, 3. You have two length 3 loops. Yeah, you just calculate. The other things are also length, also 2. This is length 4. This is length 5. That is my calculation. So this is my calculation. Number of this is the number of length n loops, always 2. So this is your series. You get this series, you calculate the root of 1 minus this square. You take a root, you take a minus log, you have your entropy. Yeah. So I should stop. Thank you very much.
Thank you for our speakers. Thank you very much for a wonderful talk. Are there any questions from the audience for the speaker? Any questions out there? All right. Well, seeing no questions, let's thank the speaker again for a very interesting talk.
May I have one question?
Of course. Yeah.
About this ergodicity, what will happen if we take a not harm measure? For example, Bernoulli measure or some kind of some deformations of the harm measure. Is it possible to connect this minimality with this kind of ergodicity with other kind of measures?
If you take the minimality, you have a unique ergodicity. So you have only one measure. If you want to take another measure, you should go like this. This chaotic part, you can construct a Bernoulli measure, many measures. You have many invariant measure. But for the minimal part, you have only one, the harm measure.
Yes.
Yeah.
Thank you.
Thank you.
Thank you. Any other questions from the audience? All right. Well, if not, let's thank the speaker again. Thank you very much for a very interesting talk.
Thank you. Thank you.
We will be back in 5 minutes with our next talk, Invariant Norms of the p-Adic Schrodinger Representation by Amit Ofer. So hang out here for the next 5 minutes, go find a coffee or a beer, and we will get started in just a little bit. Thank you again for a wonderful talk.
Thank you. So I stop my sharing.
Yeah, if you stop your sharing.
This one countable, is it published somewhere or not?
No, it's in preparation. So not yet. But, maybe this year we can put on the archive. We have some another parts I did not talk about. It's not only in this example. So there are some other things inside. So it should be a bigger paper. So we need more time to prepare.
Not ready yet.
Not ready yet. Yeah.
But it's very interesting.
Thank you. Thank you. So yeah, if you have any question, you can send me email. Yeah. Let me. Oh yeah, how to stop? Okay.